Hello class, this is Ms. Riggins with today's video on section 7.3, graphs of sine and cosine. As you're watching the video, please remember to take down notes, write down any important information, equations, formulas, or statements, as well as any questions you may have. Feel free to pause, rewind, or even replay the video as often as you need to get a better understanding. And when you're finished watching the video, write down a brief summary of the video, as well as any top questions, and submit that summary and the top question via the online WISC the day before class. All right, if we're ready to begin, let's start. We're talking about the graphs of sine and cosine. And if you remember, cosine and sine represent functions that depend on, in this case, the position of a point on a circle, where theta represents the angle the point makes with the circle. So here we have a bunch of different values in increments all throughout the 360 degrees of a circle. And if I want to evaluate the x-coordinate and the y-coordinate of a point P on that unit circle, then I would need to evaluate cosine of that angle and sine of that angle respectively. So I can go to my calculator and get these values as well. But before we start, I want to point out that there are more than one way to measure the angle of rotation. We are used to measuring them in degrees, but there's another format called radians, which we'll learn about separately. But sometimes your calculators are already set in radians, and then we would get an incorrect answer if we're expecting it to be in degrees. So in order to change this, all we do is we double click on that power battery thing, and where it says angle, we change it to degree, and we say make default. So it's going to open, and this is going to update all the open documents, and as well as any new documents and the scratch pad all at once. Okay, so that's important. I've named this variable angle value, angle V. So if I want to determine the cosine of that angle, as I type COS in the calculator, it goes from italic to not italic. Let me show you that again. Italic means it doesn't recognize the function name. Non-italic means it does recognize the function name, and we put in the input, which in this case is angle V. Okay, and when I hit enter, it gives me an approximate values, and I do the same for sine. Gives me approximate values as well. I want to point out that some of the values are exact, whereas some of the values are approximations. And if we look at our table, we see that this has also produced some approximations as well as some exact values as well. It's interesting to note that there are some repetitions here. There are basically 5 numbers that are being repeated, which are 0, 1, 0.87, which is an approximation, 0.71, and 0.5. Okay, and they're being repeated throughout all the angles of the circle, and in various positive and negatives. Okay, so it's important to know these are the values. So if I were to plot these values and connect them with curved lines, as we saw last video, we would get something that looks like this, which by definition are the general parent function of the sine function, the cosine function. And some of you may notice that these look very similar, the top one being the sine function, and the bottom one being the cosine function. And the curves are the exact same. The only difference is that one is a transformation of the other. So basically it's like I'm moving this function to the right 90 degrees or left 90 degrees. I'm moving this function to the left 90 degrees or right 90 degrees to get the same function. But they are different functions even though they're the same curve. So what do we notice about these functions? Well, first of all, the domain is all real numbers. Interesting enough to note. We also note that the range, is the numbers from -1 to 1. And that it has something to do with the amplitude and the fact that the midline of these functions is at the x-axis. Okay, and then let's talk about the symmetry, because even though if I were to reflect this graph across the line x equals 0, if I reflect this graph over this part, it would be the exact same graph. And that's because the cosine function is symmetric about the y-axis, and we call that even. So this is an even function. And I like to recognize even as your eyes are even. So it's on the same side, and your nose is the y-axis. So that's even. But then what if I reflect it across an axis, it's not the same, then that's a non-even function. There's also a definition of a function called odd, or that's reflection symmetric about the origin. And as you can see here, if I were to consider this point and reflect the graph across this point, then I would get a, then I would get the same function, and that would be that it's an even function. The graph would be a reflection on top of it. And so an even would, sorry, did I say even? I meant odd. Sorry, I'm distracted. So this function right here is not even because it's not symmetric about the y-axis, but it is an odd function because if I were to reflect it, one function here, the I would be down here, which would be odd. You have an odd looking face. Okay, anyway, that being said, we'll talk more about that throughout the semester, the difference between even and odd functions. So the domain, the range is obvious to see. You may have learned something new about the functions in the symmetry. And the functions by definition are periodic, and they are periodic because they repeat every 360 degrees, okay? And there's a definition for periodic, which we talked about last video, but it's important to note that this relationship will hold for all periodic functions where C is a value for which the function repeats itself. Now, it's important to note that in this case, it's 360, but I could put 720, I can put 1010, any multiple of 360 in here, and it would work. But when we consider the period, we want the period to be the smallest positive number possible. So that's why our period is 360. The graph repeats itself. The function repeats itself after every 360. Now, some of you may say, oh, it looks like it repeats itself after every 720, and that's correct, but the smallest value is 360. All right, so let's take a look at a function, if you recall, a unit circle, if you recall. And as we know here, if you recall that the position P, let me put this P, on the unit circle, which is the smaller circle inside, can be found by taking the cosine of the angle. I guess I should have put theta. And the sine of theta would be the y-coordinate. Okay, make this a little bit bigger so you can see. And that's from last video. If you don't remember that or why that's the case, check the last video. But let's see, we have another circle, which is a lot larger, even though the center is at the origin. But in this case, the radius is not 1 like in the unit circle. The radius is some value, and we're going to say r. How does that relate to our situation? Well, we still will need to be able to find the position by using the angle, and we can still find the x position by using the cosine. Okay, but now remember, cosine is adjacent over hypotenuse. So that would mean that now, since the hypotenuse is no longer 1, but r, then our function will look a little bit different, and it does. So in fact, the difference is that x value is now r times cosine theta using the right triangle trigonometry, and the y value is r times sine of theta as well. Okay, so it's the exact same thing except for a larger circle, which means the radius is larger than 1, or any radius that's not 1, we have to use this formula. So this is very, very important for you to remember. It's not just cosine theta and sine theta, it's actually r cosine theta and r sine theta. And as you can see, it holds no matter what r is. So that concludes the video, and I'll see you in class. Have a good day.